Greetings from MWN.com. Dr.M.Wilson, formerly Vice Principal and Head of Department of Commerce, Scott Christian College, Nagercoil is delighted in presenting this session. Thank you. Please subscribe the channel MWN.com. Chapter 17. Analysis of Variance. Analysis of variance is a statistical technique most commonly used in the field of research. It is otherwise called as ANOVA. This technique was developed by R.A. Fisher during 1920. This method can be applied for research in economic, business, psychology, sociology, education, biology, etc. ANOVA technique is applied when one wants to compare the significant equality of more than two samples. The significance of one sample with the population, two samples of a population or two samples of the different populations can be studied with the help of statistical tests like z-test and t-test. But when one wants to study about the significance of more than two samples of a population or significance of more than two samples of different populations, ANOVA technique is the most suitable test for it. ANOVA technique is based in the variances of more than two samples to decide the significant equality or inequality of the different samples. The variances are considered as an important parameter for this test. It finally states whether the different samples are significantly related or not. ANOVA technique can be used in different fields of research. Example 1. The study about the application of different fertilizers and the impact of it on the production. 2. The impact of the different types of fish feeds. 3. Performance of different types of machines. 4. Performance of different sales managers. 5. Performance of different nurseries, etc. The above studies are concerned with more than two samples. The average of the performance of different samples and their variances should be calculated. They are used for ANOVA test to find out whether the variances of different samples are significantly equal or not. If they are significantly equal, it means there is no difference in the performance. If they are not significantly equal, it means there is difference in the performance, i.e., any one method or type may be superior to others. Technique of analysis of variance. The important test applied for ANOVA is called F-test. This test is the ratio of the variance between the sample and variance within the sample. If the calculated value of F-test is within the table value of F, then it can be stated that the samples are significantly related. If the calculated value of F is greater than the table value, then it means the samples are not significantly related. The techniques for analysis of variance can be classified into two categories on the basis of the number of factors taken into consideration for the analysis. They are stated as follows: I. One-way ANOVA, one-way classification, and 2. Two-way ANOVA, two-way classification. One-way ANOVA. One-way ANOVA is otherwise known as one-way classification. This method is applied when only one factor is taken into consideration. In one-way ANOVA, one factor which influences different categories is studied. The null hypothesis in this technique is that the variances of different samples are equal. Steps for one-way ANOVA. The important steps for one-way ANOVA are as follows. 1. Calculation of variance between the samples. 2. Calculation of variance within the samples. 3. Calculation of the value of F. 4. Comparison of the calculated value and tabulated value of F. 1. Calculation of variance between samples. The following steps should be adopted for calculating the variance between samples. 1. Find out the means of each sample. For example, if there are 4 samples, then there should be 4 sample means. 2. Find out the mean of sample means. It is called grand average, and represented as connex double bar. 3. Calculate the deviations between the means of different samples and the grand average. 4. Calculate the product of number of variable and square of each deviations and find out the sum of it. 5. Calculate the variance between the samples by dividing the sum of the square, with the degrees of freedom. Degrees of freedom equals total number of samples, 1, that is, n1. 2. Calculation of variance within the samples. Variance within samples can be calculated as follows. 1. Find out the mean value of each sample. 2. Calculate the deviation of variables in each sample with their respective mean value. 3. Calculate the square of deviations of variables in each sample with their respective mean value. Then calculate sum of such squares. 4. Calculate the sum of all the sum of squares so obtained like in step E. For example, if there are 4 samples, the sum of the square of the 4 samples should be added. 5. Calculate variance within sample by dividing the sum of squares of deviations with the difference of the total number of variables in all the samples and the total number of samples. Suppose there are 4 samples each representing 9 variables, then, the variance within the sample is represented here. N equals total number of variables in all the sample, i.e., N1 plus N2 plus N3 plus N4. N equals number of samples. In this example, the total number of variables equals 4x9 equals 36 and total number of samples equals 4. Therefore, variance within sample for the example is mentioned here. 3. Calculation of the value of f. Value of f can be calculated by dividing the variance between the sample with variance within the sample. 4. Comparison of the calculated value of f with the table value of f. Table value of f can be known from the f distribution table on the basis of degrees of freedom and required significant level. The degrees of freedom are denoted as V1 and V2. Degrees of freedom for variance between the sample is V1 and degrees of freedom for variance within the samples is V2. V1 equals N1, V2 equals N. N equals total number of sample, N equals total number of variables in all the samples. If the calculated value of f is less than the table value, then the null hypothesis can be accepted. It means that the populations have the same variance. It can be stated as the samples are significantly equal or related, or the difference is not significant. It can also be stated that the samples have been drawn out from the same population. Illustration 1. A study has been conducted to find out the variations in the growth of fishes in different farms. Samples of 5 fishes are selected from 4 different farms and the length is measured and the data of the length of fishes are stated as follows. Apply ANOVA test and find out whether there is any significant difference in the growth of fishes in different ponds. Solution. Null hypothesis. There is no significant difference in the growth of fishes in different ponds. Calculation of variance between the samples. 4-column table should be prepared and values as given in the illustration should be recorded. Additionally, 2 rows should be prepared and of the first one of that sum of all the values of the column should be calculated and recorded. In the last row, arithmetic mean of all the sums should be calculated. It is calculated by dividing the sum values with 5. Grand mean is mean of means. It is calculated by dividing the sum of all the 4 means with 4. It is calculated as 15. Total variance between samples equals 50. Mean variance between samples equals 16.67. Calculation of variance within the samples. 8-column table should be prepared and values as given in the illustration should be recorded in columns 1st, 3, 5, 7. In columns 2, 4, 6, 8 the square between x minus x bar for respective farms 1, 2, 3, 4 should be calculated. The sum of such values for the 4 farms should be calculated. Total of sum of squares within the sample equals 30 plus 30 plus 50 plus 26 equals 136. Mean variance within the sample equals 8.5. N equals total variables of samples, N equals number of samples. F equals 1.96. Table value of F can be known through D, F and significant level. V1 equals degrees of freedom of variance between samples equals N minus 1 equals 4 to 1 equals 3. V2 equals degrees of freedom of variance within samples equals N equals 20 to 4 equals 16. The table of F at 5% significant level equals 3.24. ANOVA table for the above problem can be prepared as follows. Since the calculated value is less than the table value, there is no significant difference in the growth of fishes as different type of ponds. Shortcut method for one-way ANOVA. Shortcut method for calculating one-way ANOVA can be adopted when the means of the samples or mean of means of the samples are not an integer. The calculations with non-integer figures are not convenient one for direct method. Moreover, the direct method requires more time than shortcut method. Steps for calculating one-way ANOVA by shortcut method. The steps for calculating one-way ANOVA by shortcut method are as follows. 1. Calculate the correction factor by dividing the square of sum of all the samples with the total number of samples. That is, correction factor equals t square by n. 2. Calculate total sum of square. For this purpose, calculate square for each items of all the samples and find out the total of such squares for each sample, i.e., for each column. Then calculate the total sum of square as follows. That is, total sum of squares equals sum of all the squares meant for all columns, correction factor. 3. Calculate sum of squares between the samples. In this respect, first of all the average of the sum of squares meant for all columns, all samples, should be calculated. Then the sum of all these values should be calculated and it would be deducted by the correction factor. For example, if there are 4 samples, then the sum of squares between the samples can be calculated as mentioned here. 4. Find out the sum of squares within sample by deducting the sum of squares between samples from the total sum of squares. 5. F ratio can be calculated by dividing the sum of squares between samples from the total sum of squares. Illustration 1 can be worked out by shortcut method as follows. 8-column table should be prepared and values is given in the illustration should be recorded in columns 1st, 3, 5, 7. In columns 2, 4, 6, 8 the square for respective values in columns 1st, 3, 5, 7 should be calculated. The sum of such values for the 4 farms should be calculated. Correction factor equals 4500. Total sum of squares equals 1010 plus 875 plus 1330 plus 1471 4500 equals 4686 4500 equals 186. Sum of squares between samples equals 50. Sum of square within sample equals total sum of squares between sample equals 186 to 50 equals 136. Mean variance within the sample equals 8.5. N equals total variables of samples, N equals number of samples. Mean variance between samples equals 16.67. F equals 1.96. Table value of F can be known through D, F and significant level. V1 equals degrees of freedom of variance between samples equals N-1 equals 4 to 1 equals 3. V2 equals degrees of freedom of variance within samples N equals 20 to 4 equals 16. Table of F at 5% significant level equals 3.24. Since the calculated value is less than the table value, there is no significant difference in the growth of fishes as different type of ponds. Coding of data. Coding of data means simplifying the data for the convenience of calculations. If the data of analysis of variance are reduced or increased, it would not affect the value of F ratio. But all the data should be increased or decreased by a common value. Data may be increased or decreased by multiplying or dividing them with a common figure. Data can also be added or subtracted with a common value. Normally the data with large digits are reduced by deducting all the data with a common figure. Illustration 2, a new brand of fertilizer was used in 4 different type of lands. The output of the 4 lands I, 2, 3, IV in terms of number of mangoes are given as follows. Find out whether there is any significant difference of the yield of mangoes in the 4 plots. Solution. The data given in the problem can be coded for convenience of calculation. It may be reduced by deducting them by 300. The coded data are stated as follows. Codification of data. 4-column table should be prepared. In each cell the values should be deducted by 300 and written. Calculation of F by shortcut method. 8-column table should be prepared and values is calculated as per the previous table should be recorded in columns 1st, 3, 5, 7. In columns 2, 4, 6, 8 the square of values given in columns 1st, 3, 5, 7 should be calculated. The sum of such values for the 4 farms should be calculated. Correction factor equals 8,888.17. Total sum of squares equals 498 plus 857 plus 274 plus 187 888.17 equals 927.83. Sum of square between samples equals 1045.67 888.17 equals 157.5. Sum of square within sample equals total sum of squares between samples equals 927.83 157.5 equals 770.33. V1 equals degrees of freedom of variance between samples equals N1 equals 4 to 1 equals 3. V2 equals degrees of freedom of variance within samples equals N equals 24 to 4 equals 20. Mean variance between samples equals 52.5. Mean variance within samples equals 38.52. ANOVA table is as follows. F equals 1.36. Table value of F for V1 equals 3 and V2 equals 20 is 3.10. Since the calculated value of F is less than the table value, there is no significant difference in the output on different types of plots. Two-way ANOVA. Two-way classification. In two-way ANOVA the variance of data due to 2 factors can be studied. The data are classified into 2 different factors or criteria. Examples for two-way classification. Production of fishes may be classified according to different nurseries and according to different seasons. Sales of a company may be classified according to different cities and according to different salesmen. Growth of plants may be studied on the basis of different variety of seeds and on the basis of different type of soils. Two-way ANOVA explains whether these two factors under study are associated or not, that is, same or different. Steps for two-way ANOVA. The steps for ascertaining two-way ANOVA are as follows. 1. Calculate the total for all the sample variables. It can be denoted as T. 2. Find out the correction factor. That is, correction factor equals T square by N, where N equals total number of sample variables. 3. Calculate the square of all the sample variables and find out the sum of square. It can be denoted as SS. 4. Calculate sum of square of deviations for total variance. It can be calculated by deducting sum of square of all sample variables by the correction factor. It can be denoted as SST, i.e., SST equals SS, T square by N. 5. Calculate the totals of different columns, then find out square of each totals and then divide each squares by respective number of variables in each column. Calculate the total of it. Then subtract the total with the correction factor. It can be denoted as SSC. 6. Calculate the totals of different rows, then find out squares of each totals and then divide each squares by the respective number of variables in each rows. Calculate the total of it. Then deduct the total with the correction factor. It can be denoted as SSR. 7. Calculate sum of square of deviations for residual or error by deducting from total sum of squares by the sum of squares between columns and sum of squares between rows. It can be denoted as SSE. That is, SSE equals SST, SSC plus SSR. 8. Find out the degrees of freedom. Degrees of freedom can be calculated as follows. Degrees of freedom for total sum of squares SST equals C, R1. Degrees of freedom for variance between columns SSC equals C1. Degrees of freedom for variance between rows SSR equals R1. Degrees of freedom for residual variance SSE equals C1 R1. Where C equals number of columns, R equals number of rows. 9. Prepare two-way ANOVA table as follows in order to calculate the value of F. Two-way ANOVA table is mentioned here. Degrees of freedom. For column variance, V1 equals C1, V2 equals C1 R1. For row variance, V1 equals C1, V2 equals C1 R1. 11. Compare the calculated value of F with table value. If calculated value of F is less than the table value of F, then the null hypothesis can be accepted. Hence, there is no difference in the variance of two factors. If calculated value of F is greater than the table value, there exists a significant difference in the variation of the two factors. Illustration 3. The following table shows the sample data related to the per hectare production of coffee in different type of soils and for different varieties of coffee. Per hectare production of coffee, in tons, is mentioned here. Find out whether there is any significant difference between the type of soil and varieties of coffee. Test at 5% significant level. Solution. Correction factor equals T square by N. T2 equals 4 plus 6 plus 5 plus 9 plus 9 plus 11 plus 10 plus 6 plus 11 plus 13 plus 12 plus 12 2. Equals 1082 equals 11,664. N equals 12. Correction factor equals total sum of squares, SST equals sum of squares, correction factor. Equals 1074972 equals 102. Sum of squares Bedouin columns, SSC. Equals 192 plus 300 plus 243 plus 243 to 972 equals 978 to 972 equals 6. Sum of squares between rows, SSR. Equals 144 plus 324 plus 576 to 972 equals 1044972 equals 72. Table value of F. Between column for V1 equals 3, V2 equals 6, is 4.76. Between rows for V1 equals 2, V2 equals 6, is 5.14. The calculated value of F.50 is less than the table value of F4.76 between columns. Hence, the production of varieties in coffee does not differ significantly. The calculated value of F9.00 is greater than the table value of F5.14 between rows. Hence, there is significant difference between different types of soils. Exercises for this chapter are well presented here. Please subscribe the channel MWN.com. Exercises for this chapter are well presented here. Please subscribe the channel MWN.com.